All right, so we're going to get going here with some more fun with implicit differentiation. So I'm going to take a look at a few different, see what we can come up with. We're going to be applying the things more. Last time we've just found out what dy over dx was. But what we're going to do is we're going to take something and we're going to try to figure out, like say maybe tangent lines and the slope of maybe even just the slope of the tangent line, or so we got some different things. So we got evaluate the derivative at a point, okay, which that just means that's the same. These are the equal to the slope of the tangent line at the point. They mean exactly the same thing. We do it exactly the same way. So what we want to do then is say on this one, okay, and let's say we have a point. Let's say, how about at x, at x equals -1, okay? So if we go through and like, okay, well, I'm going to take the derivative of this, and so we do d over dx. This is the derivative with respect to x. We're going to do that of both sides. And so on one side we have xy, on the other side we have 6. So if we take the derivative of xy, well, these are multiplied together, so we have to use product rule. So that's going to be the first times the derivative of the last plus the last times the derivative of the first. Well, the first one, the derivative of x is just 1. And the derivative of 6 is 0. All right, so now we have all of this. And of course, you could solve for dy over dx right now and have this. But one of the things I'm going to suggest for these problems is that we are trying to figure out what this is, and we're going to be given a point. So we want to, if you sometimes solving an algebraic equation is easier if everything is numbers except for the variable you're trying to find, which in this case is dy over dx, or unknown better, as opposed to having a bunch of other variables in there. So I think sometimes people do better. So we have x equals -1, so we have -1 goes in for x. Well, dy over dx is the thing we're trying to solve for. Y, how would we figure out what y is? Well, to figure out what y is, you just back into the original problem, because the original problem says the relationship between x and y. If x equals -1, that means we have -1 times y equals 6, means that y equals -6. So that means we have -6 here equals 0. So we end up, we'd have -1 dy over dx equals 6 when we add 6 to both sides, and dy over dx equals -6. So this is the derivative at the point. This is the slope of the tangent line at the point. And if we wanted to find the equation, what do you need for the equation of a tangent line? Two things, slope and point. Well, we already have the slope. We did that. M equals -6. And we already have our point. We did that. -1 comma -6. So we just take those things together and we end up with equals slope times x minus x1, or plus 1 in this case. And so we go. And so we're here. This ends up being our equation. Or, of course, if you want to distribute, then you have -6x minus 6 minus 6, or y equals -6x minus 12. And so you get your equation of your tangent line. So sometimes we just want to stop here. Sometimes I'll have us go through the rest. Just pay attention to what's going on with the words. All right. Let's try a little bit more complicated one. How about x squared plus y squared equals 4x squared y. And we're going to go at the point 1, 1, 1. So 1 comma something. All right, we got to figure out what that something would be. Oh, no. All right, how about this? Okay, I'm gonna let you know that there is a point such that x equals 1, where the tangent line is horizontal. Okay, and we're going to figure out where that what the coordinate will be based off of that. So in this, well, this tangent line is horizontal. What's that mean? Well, that means that the derivative of dx equals 0 when x equals 1. So what we want to do then, kind of go about a couple ways, but my first thought is find the derivative, and we want to figure out, okay, well, what would y have to be when x equals 1 to make our derivative be 0? So let's take a look here at our equation. We're going to take the derivative both sides with respect to x. And I know it looks messy, but that's why I picked it. So that way we can do a messy one. And all right, so first we take the derivative of this. This is a chain rule problem. So you have the 2 to the front. The inside stays the same. 2 minus 1 is 1. Times the derivative of the inside, which would be 2x plus 2y. And you can also write it, instead of writing dy over dx, you can also write it y prime. So we can do that. All right, equals, and now we're going to use this. This is a product rule one. So it's the first, 4x squared, times the derivative of the last, which is y prime, plus the last times the derivative of the first, which would be 8x. All right, dy over dx, which is another way of saying y prime, is going to be 0. So what we could do is we're going to put in 0 for all the y primes, and for every x, we're going to put in 1. So we'd end up with 1 plus y squared, 2 times 1 plus 2 times y times 0 plus equals 4 times 1 squared times 0 plus y times 8 times 1. And so every x we change to 1, every y prime we change to 0. And that was the only variable in here, y. And so we want to solve for y using this, okay? So this ends up being, we get 2, we distribute in that, 2 times y squared. So 2 times y squared is 2y squared, so plus 2y squared. This is going to be 2 plus 0 equals, well, that's just going to be 0 plus 8y. So we end up with 8y over here. Then we distribute that and we get 4 plus 4y squared. And so now we have this. And what kind of equation is that? That's a quadratic equation. In order to solve a quadratic equation, you got to get all the everything on one side. And so we'd end up with, we go like this. We'd say 4y squared minus 8y plus 4 equals 0. Or we divide everything by 4. We'd have y squared minus 2y plus 1 equals 0. Now we factor that, we end up with y minus 1 squared equals 0. So y equals 1. So at that point, 1, 1. Now, so, but here, this is what, in this case, all this means is that if, okay, this is real important, if there is a x value where the slope is 0, then it happens at 1, 1. But we don't know if this point yet, we don't know if this point is on the curve. All we know is that 1, 1, when plugged into the derivative, makes the derivative be 0. But we don't know if 1, 1 is actually a point on the curve, or the derivative even matters. So what we have to do is we have to go and check to see, is 1, 1 on the graph? And how can we figure that out? We substitute it into here and see what happens. So we had, remember, x squared plus y squared squared equals 4x squared y. So you will have 1 squared plus 1 squared squared equals 4 times 1 squared times 1. So we'd have 1 plus 1 squared equals 4, and then 1 plus 1 is 2. 2 squared equals 4. Check. So that one does. And so that's how we could go through and do something like that. All right. And then let's take a look at maybe another second derivative problem. Okay, second derivative problem. So let's say we have y cubed equals 4x. All right, so what we'd want to do then is we want to take the derivative of both sides, because before you can get to the second derivative, you have to get the first derivative. So y cubed would be 3y squared dy over dx equals 4. Meaning that dy over dx equals 4 over 3y squared. Now this is going to be important to hold on to. Okay, now what we want to do is, that's our first derivative, so we have to take the derivative again. So d over dx to both sides. Now on this side, we're going to we write d squared y over dx. That's how we write that. Over here, okay, kind of look at it a couple of different ways. But what would probably be the easiest is to rewrite this with a negative exponent. So what would that look like? That'd be 4 over 3, 4/3, y to the negative 2. And if I'm going to take the derivative of that, isn't that a lot easier than using the quotient rule? I think so. So we'd end up with negative 8 over 3, because negative 2 times 4/3 is 8/3, y to the, subtract 1. Negative 2 minus 1 is negative 3. But since y is not x, what do we need? We need dy over dx. Now the problem is we don't want to leave dy over dx as dy over dx for the derivative. So what we're going to do is we're going to now go back up to here, and we're going to substitute that in. So now we have negative 8/3 y to the negative 3, which now we can move that back down to the bottom. Dy over dx, which was 4 over 3y squared, from right there. Multiply straight across, we end up with negative 32 over 9y to the 5th. And this comes out to be d squared y over dx squared. Now this would be, I imagine they could get pretty funky with that. I mean, there's some things that we could do, but the worst possible scenario is, they would, just so you know, I mean, this is just a thought. We could write it as negative 1/9, and then we'd have 2 over y to the 5th. I mean, that's a possibility because 2 to the 5th is 32, but I doubt that. And anybody who has taken some basic programming classes and should know that y 2 to the 5th is 32, because that's how binary works. Remember how you count on your hand? You can count on your one hand to 31. That's because 2 to the 5th power is 32. So anyway, all right. And, just want to give you some problems to practice. So try and see. Let me know if there's anything else we want to look at. Thanks.